So like I just said, a differential equation, that's what we're talking about today. A differential equation is just an equation that involves a derivative. Differential equations can have what we call different orders. And so the order of a differential equation is just the highest derivative involved. So in this particular differential equation that we have below, it has a derivative in it, and it has only a first derivative in it. So we would say that it is a first order differential equation. We might have some where we have a second derivative or a third derivative in the equation. Those would be second or third order differential equations. Easy enough? Terminology wise there?
Yeah.
Okay. Now, you're going to say this is exactly the same as what we were doing before. And pretty much you're right. What we're doing is we are looking for all functions that satisfy this. That's how you solve a differential equation. So look for all functions that could have this as its derivative. Well, all we have to do that is take an antiderivative of both sides of it. So the antiderivative of dy dx, that's just the antiderivative of the derivative of y, should just be
y.
And the antiderivative of this side, well, secant squared should be
tangent.
Really, we bring this dx over here. Should be tangent x, and then the derivative or the antiderivative of the 2x should be x squared. The derivative of the 5 should be 5x, and we throw a constant on it. No different than what we've been doing, except now instead of me just saying what's the antiderivative of this function, we're saying solve this differential equation. Dy dx is this other function. So look for all functions that have that as its derivative, and this is that. This is all of the functions that have secant squared x plus 2x plus 5 as its derivative. Okay? We call this the general solution to the differential equation. It's called a general solution because it's got this plus constant on it, and there is no initial condition that we are saying that our function has to satisfy. So anytime you're asked to find the general solution of a differential equation, this is all you're going to do. You're just going to anti-differentiate, put your constant, and call it good. Easy enough?
Yeah.
If we were given a value that y was supposed to equal, would we just solve for c?
Yep, that's exactly what we would do, and that is exactly what we will be doing shortly. So right here, when we have initial conditions, like I'm going to give you here, we call the problem sometimes an initial value problem, and it has one particular unique solution. And so rather than finding a general solution, we'll be finding the particular solution to the differential equation. So now we are interested in the particular solution to this differential equation, dy dx equals e to the x minus 6x squared. But we want the graph to pass through the point 1, 0. So that's an initial condition. We know that for y, for our solution, we know that when x equals 1, y needs to equal 0. And so we have to make that true with the differential, or with the equation that we get when we solve the differential equation. Okay. So all we do, same thing, take an antiderivative, right? We'll bring this dx over here so that it becomes now an antiderivative of dy, which is y, and an antiderivative of e to the x minus 6x squared. And so what's the antiderivative of e to the x?
E to the x.
E to the x. And the antiderivative of minus 6x squared?
2x cubed.
Should be what?
2x cubed.
2x cubed. And we do have to add still in our constant. Okay? But then once we've added in our constant, now we will go in, take our initial condition, that when x is 1, y is 0, we'll plug in 1 for x, and we'll plug in 0 for y, and see what the constant is. So if we do that, we end up with 0 equals e to the first, which is just e, minus 2 times 1 cubed, which is just minus 2, plus our constant. And so if we solve for c, we would find out that c is equal to what?
2 minus e.
2 minus e. And so what we'll do is we'll just go back in, we'll rewrite this now, and we'll say our final solution is y equals e to the x minus 2x cubed plus 2 minus e. And that, if we take its derivative, is still e to the x minus 6x squared, because the plus 2 is a constant and the minus e is a constant, and they go away. And if I plug in 1 for x, I get e minus 2 plus 2 minus e, which is 0, and that's exactly what I should get. Good or no?
Good.
That's the very, very basics of differential equations. They do get more difficult than this, but that's the whole idea of it. We're not going to really change much and go away from this idea of what a differential equation is. Yeah, that's what we're going to be doing. So let's do another one. We want to find the particular solution to dy dx equals sine x plus 2x, and we want to have a y-intercept of 3. So what does a y-intercept of 3 tell us that the initial condition is?
It passes through the point 0,3.
Right, this is the point 0,3, so that when x is 0, y must be 3. So we'll just anti-differentiate both sides of this to get y equals what? What's the antiderivative of sine?
Negative cosine x.
Negative cosine. And the antiderivative of 2x?
X squared.
Okay. Plus,
3.
not plus 3 necessarily, but plus c, right? Plus our constant. And then we have to figure out, based on this, when x is 0, what gives us a y value of 3. So be careful with that, because the cosine in there is going to change that around. If this was just a polynomial and it was x equals 0, then our constant would definitely be 3. But since it's not just a polynomial, we got to actually go and solve it. So we know that 3 needs to equal negative cosine of 0 plus 0 squared plus our constant. And what's the cosine of 0?
1.
1. So this is 3 equals negative 1 plus c, or c equals 4. Good. So our final answer should be y equals negative cosine x plus x squared plus 4. Good or no?
Good.
All right, and we could see that if we did take the derivative of that, the derivative of negative cosine is positive sine, derivative of x squared is 2x, and the derivative of 4 goes away. All right, let's do another one here. You guys want to do this one on your own?
Yeah.
All right, I'll give you guys, what, 2 or 3 minutes here? Probably won't even take that long, but I'll give you 2 or 3 minutes and let you work through that one. Ready, go. All right, so hopefully you took your antiderivative, and what'd you get for your antiderivative to start with? Y equals
X squared over 2.
x squared over 2, that's the antiderivative of x, and then minus
Tangent x.
tangent x, and then plus our constant. And then when y is 3, x is 0. give us for our constant? Should just be
3.
3. And so you end up with y equals x squared over 2 minus tangent x plus 3. And you put that in a box and felt really good about yourself, right?
Uh-huh.
Yeah, that's wonderful until the part where I tell you that you're not quite completely right. Bummer, huh? Nothing wrong with what you did. There's just something else we have to add to this one. What's different about this final function that we ended up with, x squared over 2 minus tangent x plus 3, than all of the ones we did previously? Anybody have an idea? All right, what was the first one that we did? What was the first equation that we got for the very first differential equation we did?
Tangent x plus x squared plus 5x.
Which one? That was the first one, was tangent?
Do you mean the derivative or?
No, the very first, sorry, the very first, I'll go back to it. I'll just look at it. That way I make sure I get what I wanted. Oh, sorry, not the very first particular solution we did, not the very first general, the very first particular one we did. This one, we got e to the x, right, minus 2x cubed plus 2 minus e, right? That's a nice looking function, isn't it? It goes pretty far down there, yeah? Nice looking function, isn't it?
Beautiful.
Yeah, it's really nice, right? I can plug any number all the way to negative infinity, plug in any number all the way to positive infinity, no discontinuities, nothing weird happening, just a nice, regular, good old function, yeah? Yeah. What about the next one? What was the next one?
Negative cosine x plus x squared plus 4.
Negative cosine x plus x squared minus 4 or plus 4? Sorry. Plus 4? Plus 4, okay. Oh, look at that one. That's a nice looking function too, isn't it? Let's see, we'll zoom out a little. Looks like I could plug any number to negative infinity or infinity in. Nice, pleasant little continuous function, right? Nothing weird, nothing strange about it, just a good old regular function. What about the one that we just did? What did we get? We got x squared over 2, right? Was it plus or minus the tangent x?
Minus.
Minus, okay, minus tangent x and then plus 3, right? How about this function? Is that a nice normal looking function?
No.
No, not so much. It looks very different from the other one. What's different about this one?
There's like a ghost of a parabola.
A ghost of a parabola?
Yeah.
A ghost of a parabola. I've never heard that before. That's interesting. How so? That like these sort of like shape a parabola where the weird thing is happening in here?
Yeah, it kind of has the outline.
Yeah, sort of. Yeah. That's sort of has an outline of like an x squared over 2 plus 3 sort of thing, doesn't it? Yeah, that's true. I would have never described it as a ghost of a parabola, but I like that.
It's like the negative of a parabola. Like everything else is filled but the parabola.
All right. Yeah, that's reasonable. All right. Yeah, I like the description. That's not the thing that I'm having an issue with, though, is this ghostly parabola. What's the thing that I'm having an issue with? I do like the ghostly parabola, which is why it's not an issue, because I like that. Can I plug any number into this and get a value?
No,
for
because
example-
there's
Okay, go ahead.
there's asymptotes.
there's asymptotes to it, right? There are discontinuities. In fact, there are an infinite number of vertical asymptotes to this because of the tangent function, because tangent itself is not continuous for all real numbers. Okay? And obviously you wouldn't have known this because I hadn't told it to you yet, but now that I'm telling it to you, whenever there are discontinuities in your graph of your solution to your differential equation, you have to go in and you have to specify where this solution is valid. And this solution is valid only on the specific continuous portion of the function that includes your initial condition. So I'm going to write this over here. A particular solution to a differential equation is only guaranteed, oh, that's not a U. There we go. Is only guaranteed to be valid on the continuous portion that includes the initial condition. This is very important, or else you will miss points on my quizzes and on the AP test. So what that means is I'm only guaranteed that this constant has to be that constant on the specific interval that includes that point. I could have a totally different constant. I could have plus 1,000,000 on every single other interval of this function that doesn't include that initial condition, because the only place where it has to be plus 3 is where we get this. Does that make sense to everybody?
Yeah.
So we're just getting the interval that includes 0,3.
Exactly. So we have to figure out what interval can include x equals 0. So where are there asymptotes for the tangent x part? We know there's one at pi over 2, right? X can't be pi over 2, x can't be 3 pi over 2. What about in the negatives? X can't be negative pi over 2, right? Negative 3 pi over 2, and so on. So what interval is it continuous on that includes x equals 0?
Would you just say from negative pi halves to positive pi halves?
Yep. So we'll say that x equals 0 falls between negative pi over 2 and pi over 2. So we will say this is valid only on negative pi over 2 to pi over 2. Good or no? And that needs to be included as part of our solution. And so we'll note that this one's valid from negative infinity to infinity. There were no discontinuities. Same here. No discontinuities here, right? This one was a general solution, so we don't have to worry about an initial condition at all, even though there were asymptotes. It's valid for everything because plus c is not a specific function. But the ones where we have a particular solution, if it's not continuous for all real numbers, you need to find that interval in which it's valid. And in this one, since it's not continuous because of the tangent, we have to find it. Good or no?
So if our initial derivative had, let's say, like an irrational equation in there, we would have to do the same thing with the integral or the base equation. I don't know how to word it.
No, you do not have to. It does not matter about your original derivative. So like secant has discontinuities, and I mean, in this case, secant has the same discontinuities as tangent does. But if somehow you ended up with a function up here like cosecant, but you ended up with a tangent down here in your answer, and there were different discontinuities, you don't need to worry about the ones from the original differential equation. You only need to worry about the discontinuities in the solution to your differential equation. Does that answer your question?
Yes.
Just making sure. All right, cool. So we got a couple minutes here. Let's do another one. And this one, my guess is you will note that this has some discontinuities when you differentiate it. And so I'll give you guys a chance this time to work through this one on your own and see if you can get the correct interval of validity on your own. So I'll give you 2 or 3 minutes, then we'll go through it. And this will probably be the last one we do today. So I'll give you a couple minutes. You guys think you could do that?
Sure.
Wonderful. All right, ready, go. So you integrated both sides to get a equals, right? What'd you get on the right-hand side? One over t became what?
Natural log of absolute value of t.
Good. And then what about minus 1 over t squared, or minus t to the negative 2?
Plus 1 over t.
Plus 1 over t. And then the plus 6 becomes a plus 6t, right? Plus a constant. And so then we solve for our constant. So when a was 0, t was 1. And what does that give you as your constant?
-7.
Good. Everybody agree with that? Right? This natural log of 1 is 0, right? This is just a 1 and a 6. 7 plus c is 0. Yep. And so our final result here should be a equals natural log absolute value t plus 1 over t plus 6t minus 7 for, let's see, where are discontinuities on this?
When t equals 0, right?
Right, t cannot be 0. So we have either an option of negative infinity to 0, or we have 0 to infinity. And which one of those will include t equals 1?
Zero to infinity.
Wonderful. So this is the answer we should have gotten. A equals natural log absolute value t plus 1 over t plus 6t minus 7 or 0 to infinity. Everybody good there?
Yeah.
Wonderful. All right. That's, I think, good enough for today. We will stop right there.